Thermodynamics is a topic that contains a lot of calculations, but also plenty of easy to lose 1-mark questions where you need to recall a key definition or a fact from the specification. This video is the 8th in a factual recall series designed to help you ensure that you can recall those key definitions. There's a link in the description below to all of the questions so that you can answer those and then use this video to check your answers. An enthalpy change is the change in heat energy that is measured at constant pressure. When we talk about standard states, we're usually talking about 1 mole, whether that's 1 mole of a product being formed, or 1 mole of a fuel being burned, or 1 mole of atoms losing 1 mole of electrons. It's normally happening at 100 kilopascals, so normal atmospheric pressure, and it needs to be happening at a stated temperature. If this isn't given explicitly in the question, then we assume that it's 298 Kelvin. But actually for these enthalpy changes, it doesn't have to be 298, we just need to know what that temperature is, because obviously the enthalpy change will be different at different temperatures. The enthalpy change of formation can be defined as the enthalpy change when 1 mole of a compound is formed from its constituent elements, so in other words the elements that make it up, under standard conditions, with all reactants and all products being in their standard states. That last bit is really important because it very regularly gets missed out by students, and for the AQA exams at least, you do need it for the mark. Now, as we've just said, it's important that when we're defining formation, we're talking about 1 mole being formed. So hopefully you've managed to write an equation for the Haber process, but crucially, we need to only be making 1 mole of ammonia, not 2. So if you've written this as N2 plus 3H2 making 2 moles of ammonia, then that's not correct because we need to only be making 1 mole. It's also really important that you have your state symbols in there to show that everything is in its standard states. Likewise, when we define standard enthalpies of combustion, again we need to talk about 1 mole, only this time it's 1 mole of a substance being burned rather than formed, and it's burned in oxygen, and again we need to say that all reactants and all products are in their standard states. So when we write a chemical equation here, we need to only be having 1 mole of butane being burned, and hopefully you're familiar from GCSE with how to write an equation for the complete combustion of that. So it's going to look something like this. Our first ionization energy is going to be the standard enthalpy change when 1 mole of gaseous atoms, again that gaseous is really important, is converted into 1 mole of gaseous ions with a single positive charge. So when you write an equation for this, we're going to have our aluminium, and you need the state symbol to show that it's a gas. Again, that's a really common mistake that people miss out their state symbols. And then we're producing the aluminium ion, which has a positive charge and a single electron. It doesn't matter that aluminium, when it does chemical reactions, doesn't form single positively charged ions. We're talking about the first ionization enthalpy, so therefore we're always going to produce an ion with a single positive charge. Now, it's far less likely that you would be asked to actually define a subsequent ionization energy. It's much more likely that they would ask you to write an equation which represents it. But just in case, and to be sure that you're clear in your head what we're actually talking about here, for our second ionization energy, we're talking about taking 1 mole of gaseous ions that have a single positive charge and removing another mole of electrons to form a mole of gaseous ions that have a double positive charge. So we can represent this equation like this. So again, here you can see we've got our state symbols because these have to be gaseous ions, and we've got our oxygen single plus becoming oxygen double plus, and it doesn't matter that oxygen doesn't form positive ions when it's forming bonds, because what we're talking about here is ionization. Then electron affinity you can think of as kind of the reverse of the ionization energies. So here we're talking about the enthalpy change when a mole of gaseous atoms gains an electron to form a mole of gaseous ions with a single negative charge. And again, we can write this as an equation, so we can have our gaseous atoms gaining those electrons to form gaseous ions. And again, I'm going to say it again, make sure you have your state symbols in there. In my experience, standard enthalpy of atomization often causes a lot of students to come unstuck in the exam. And strangely, this isn't because they can't remember the definition for it, but it's because in the heat of the moment they can't apply it to the data that they have. So when we talk about standard enthalpy of anything, we're talking about 1 mole. But for standard enthalpy of atomization, it's not 1 mole that we're starting with, it's 1 mole that we're ending with. In other words, we're making 1 mole of gaseous atoms, not starting with 1 mole of molecules. And even though students correctly recall this and can write out the definition, they often don't calculate appropriately. So we can define standard enthalpy of atomization as the enthalpy change that is undergone when 1 mole of gaseous atoms are formed from their molecules in standard state under standard conditions. So for instance, if we were going to write a standard enthalpy of atomization for chlorine, we need to be making 1 mole of chlorine atoms, not starting with 1 mole of chlorine molecules. So it looks a little bit like this. And again, we've got our standard, we've got our state symbols in there. Mean bond enthalpy can be defined as the enthalpy change required in order to break 1 mole of bonds in a range of compounds. That's why it's mean, why it's an average. And the answers that we get by using bond enthalpy data may be different from the ones that we get with Hess cycles because these are a mean. So because these numbers are averaged across a range of compounds, and actually the enthalpy change required to break bonds in one compound will be different from another compound because it's actually influenced by the other atoms in that compound and what else is going on around them. In addition to differences between those two calculation methods, you'll also find that there's a difference between the enthalpy change that you get when you calculate a Born-Haber cycle and look at the enthalpy change of formation for an ionic substance, and then the experimental data if you actually made that ionic substance. And the reason for this is because where you do that Born-Haber cycle, you assume that a substance is purely ionic, but actually this often isn't the case. So if that substance has some covalent character, then you're going to get a value that is not consistent with the one that you've calculated. The lattice enthalpy of formation is the standard enthalpy change when 1 mole of a solid ionic compound is formed from its gaseous ions. So again, if we were going to write an equation for this, it will be really important that we included our state symbols so that we could see that we were forming this from gaseous ions. The lattice enthalpy of formation and the lattice enthalpy of dissociation have the same magnitude, but one is negative and one is positive. So in other words, if you multiply either one by -1, then you get the other enthalpy. The enthalpy change of hydration is a theoretical concept, and it's the enthalpy change when water molecules surround 1 mole of gaseous ions. In contrast to that, the enthalpy change of solution is the enthalpy change when 1 mole of solute perfectly dissolves in just sufficient water to make a solution where the ions don't interact with one another. It's impossible for us to work out exactly what the enthalpy change is for making hydrated crystals from dehydrated crystals, because in doing this process it's impossible for us to stop some of the solute dissolving, and this would mean that our temperature changes would be inaccurate. Hess's law tells us that the energy change for a chemical process or a chemical reaction is going to be exactly the same regardless of what the route taken is. Delta H is an enthalpy change and it's measured in kilojoules per mole. A negative value of delta H tells you that a process is exothermic or that it gives out energy to the surroundings. Delta S is the change in entropy, and this is measured in joules per Kelvin per mole. A negative value of delta S tells you that a system is becoming more ordered. Entropy will increase in a situation where the system becomes more disordered. So this could be a state change like solid changing to liquid or liquid changing to gas, but it could also be a situation where the number of particles increases. If you finish doing inorganic chemistry, then you already know one really good example of this, which is the chelate effect. So you could have something like a hexadentate ligand like EDTA kicking out 6 monodentate ligands like water from a compound ion. So you've gone from having 2 species, the compound ion and the EDTA, to having 7 species, the compound ion and the 6 water molecules, and that is a massive increase in entropy and helps to explain why that change occurs quite so readily. G is Gibbs free energy, so delta G is the change in Gibbs free energy, and we measure it in kilojoules per mole. To calculate delta G, we look at the change in enthalpy, so delta H, and from that we subtract the temperature multiplied by the change in entropy, and that will give you delta G. If you have a negative value of delta G, a value that is less than 0, then this tells you that the reaction is feasible. A reaction is feasible if it may occur spontaneously. But even if a reaction is feasible, it might still not occur, either because the rate of reaction is so slow, or because even though the product is thermodynamically stable, it's kinetically unstable. If you want to calculate the temperature at which a reaction becomes feasible, you basically need to calculate the temperature at which delta G is exactly 0. So first we take delta G as being delta H minus T delta S, and then we rearrange that and we say that at the point at which delta G is exactly 0, then delta H will equal T delta S, and therefore in order to work out what the temperature is where that occurs, we can do delta H divided by delta S. It's also possible to plot the values of delta G on the y-axis against temperature on the x-axis and see where that curve crosses the x-axis, and that will be the point at which delta G is 0 and therefore the reaction becomes feasible. Thank you very much for watching, and I hope that you found that useful in your revision for A-level chemistry. If you do still want some help with those Born-Haber cycles, I have got lots of videos to help you with that as well. If you found this useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.